The square law painting function is another calculation or transformation that can be used to convert the value of our virtual pan pot into an amplitude value for the left channel and right channel of our stereo signal. Previously, we looked at the linear panning function to do this transformation. The interesting thing about the linear panning function is that it maintains equal combined amplitude between the channels regardless of what position you have on the panning potentiometer. However, the linear panning function does not maintain equal combined power. As human listeners, in many ways, we perceive the strength of the signal based more on the power rather than on the amplitude. This motivated then the creation of panning functions that maintained equal combined power while sacrificing the equal combined amplitude. We'll look more at that here, while also exploring the square law panning function. Here I'm going to demonstrate how to use square law panning. In a previous video, I showed how to start with a mono input signal and then use linear panning functions to create a stereo output signal. I'm going to continue on with this script. So after we import in the sound file, we create a new variable that represents the user-selected pan knob value. This is any number that can span the range from -100 to +100. In fact, we're going to try out several different numbers as we're testing our code. The first thing I'm going to do is shift around some of the commands that I've already written. This way I can demonstrate the generalized approach that's usually used by engineers when they're working with multiple panning functions. So here, after we read in this pan value, I've put it into this mathematical expression. This is a transformation from one scale, from -100 to +100, down to a different scale, from 0 up to 1. That's because we need to use it as an amplitude value. We don't want it to go above 1 and we don't want it to go below 0. So another way to think about doing this is to create a new variable up here and assign the result of this expression to the variable. So I'm going to call it x. So I'm going to transform the scale and put it onto x. Now I can use x and substitute it right back in here directly. So it's just as if I had this same code down here. The next thing then is I'm going to put in x instead of right amplitude. It will still give us the same exact linear panning functions. What it's going to do is open us up to the ability to transform the x value onto another scale. And that's what's going to happen here when we get to square law panning. So what I'm going to do is copy this code and paste it below. We're going to do something similar to what we had before, but we're going to change these expressions ever so slightly. So let me comment out this code that we don't need anymore. Now let's focus on square law panning. Here, we're going to put in the square root function. We're going to do the square root of x for the right amplitude and the square root of 1 minus x for the left amplitude. This is why it was so helpful for us to calculate this variable first, based on the transformation of this scale. So if we were to substitute in the endpoint values of 100, we'd end up with an x value of 1. We can put that in. Square root of 1 is still 1, so that works great. And the square root of 1 minus 1, or the square root of 0, is 0. So our endpoints are still going to be the same. What's going to be different then is what happens in between the endpoints. For instance, what if we panned to the center? We had a pan value of 0. So now if we go through, x is going to be 0.5. If we take the square root of 0.5, it's actually going to be a different number, close to 0.7. So the amplitude on the right side is now going to be higher. Similarly, we do 1 minus 0.5, that's also 0.5. So the square root is going to be identical to what we had before. So that means our signal is going to be panned to the center. However, the amplitude is going to be higher. The reason for this is engineers noticed as they were using these panning functions on a panning knob that if the signal was panned to the center and you had linear panning functions of 0.5 and 0.5, your perception was that the signal got quieter when it panned to the center. We don't want that. We want to perceive it as if no matter you're panning it to the left or to the right, that you have the same amount of energy. And this is why they started to use functions that had something called equal power. And we're going to explore that here by plotting and comparing linear panning functions and square law panning functions. We can run this script and see that things are working correctly. So over here, we'll pan it off to the right, and let's listen to the result. Now let's pan it to the center. Finally, let's pan it a little bit over to the left. So these are the functions that we can use if you wanted to perform square law panning. Let's do a quick comparison then between linear panning and square law panning. I'm going to do this by adding in a new section to our code. I'm going to call this the comparison of linear and square law functions. So here, we're going to make use of these functions, but then let's plot them and compare our results. So to begin with, let's create a new variable x. In x, instead of having a single value, let's make it an array. It's an array that can span from 0. We'll go up by a step of 0.01, and we'll end at 1. Let's remove this symbol. So this is actually an array now. We can still use it in these functions, the right amplitude and the left amplitude. So let's calculate those things down here. So we could plot, if we like. Let's go ahead and plot x versus x, and also x versus 1 minus x. Those are our linearly panning functions. So we can see what's going to happen for the right channel and then the left channel. Why don't I put in here a legend that says linear right, and then also linear underscore left. So we'll have 2 lines. Let's look at the result if we were to plot this. I'm going to comment this one out so we don't have to listen to it back. Now we can see the values that end up being used for the amplitude whenever we pan the knob to different positions. So if we pan it all the way to the left, what's going to happen is the amplitude over here on the left is 1 and it's 0. And then in the center, it's 0.5. So this is what happens if we've got the linear panning functions. Let's add to this then. Let's go in here and let's plot x versus the square root of x. And then also x versus the square root of 1 minus x. Now let's add some more things to our legend. So we'll call this one square root of the right, and also square root of the left. So let's now look at these 4 different lines and what they tell us then about the amplitude for when we use these different panning functions. All right, so in this case, we still have the blue and the red. Those are linear panning functions. And then we have the yellow and the purple. In this case, again, like I said, when we pan it to the center, the amplitude is actually higher. So in this case, the amplitude is always higher for the left square root function compared to the left linear function. Same thing on the right. So what does this allow us to do? Let's create another figure that now we can compare what is the amplitude, combined amplitude and combined power. So here, I'm going to type in figure. That will open a different figure window. Up here at the top, I'm going to put in close all so that we start out with removing all the windows. Now let's put in another plot. Let's put in plot here of x, and let's put in x plus, so this will be the combination of 1 minus x. So this one's trivial. What we're going to end up with is x minus x, we end up with 1. So that will mean that we have constant amplitude of 1 across the whole possible values, set of values. Then we're going to have x here. We'll plot that against square root of x plus the square root of 1 minus x. So that's our plot. Let's put in a legend. The first one is going to be linear, amp for amplitude, and the second one is square root amplitude. So let's run this one and look at the different amplitudes. So in this case, what's difficult to see is we actually have a blue line that has an amplitude of 1 the entire time. But then what happens is our combined amplitude is actually different. Our amplitude increases as we pan things to the center, and then it decreases again as we go off to the right. So this is our amplitude. Now let's look at the power. So the way that this works, I'm going to copy these lines of code, paste them in down before. So this now is going to be for equal power. I'm going to take this, and the way that it works is we're going to square, look at the power, this one. So we need to use, in this case, when we're working with an array and we're working with an exponent, we need to use a pointwise there, and then also pointwise here. Right, so we're squaring this function, we're squaring this one. We're looking at the combined power of these two things. Then, as you would expect, right, if we take the square root of x, and then we also square that, what are we going to end up with? X, and then same thing over here. So this one is going to be linear power and square root power. This will look cleaner if I remove these. Okay, now we can look at our third figure window and look at what's the difference in the power. So in this case, we have the red line, which represents equal power, and that's with the square root functions, but we do not have equal power when it comes to the linear functions. In many ways, the way that our ears perceive sound is based more on power than it is on amplitude. So this is a reason why many DAWs, many even hardware mixing consoles are going to use some kind of equal power panning functions rather than the linear panning functions.